Good morning, everyone. We'll talk today about constraint qualifications. So this approach by constraint qualifications are a more classical approach to optimality conditions. So I will start with geometric interpretation, and then I will get into the details of the constraint qualifications. So this is the problem again. There are some things here that are a little bit different, but it's not so different. Here we have the indexes for the equality constraints are 1 to m, and for inequalities are m+1 to m+p. We do this because in some conditions we want to mix inequality constraints with equality constraints, and this will be easier. The rest is the same. So just remembering from the last lecture, an optimality condition is anything that is fulfilled at a solution, any necessary condition for a solution. So two trivial examples is feasibility. Every solution must be feasible, and every solution must also be a local minimizer. The problem with these conditions is that the first one is too broad. So we need stronger optimality conditions. We don't want points that fulfill this condition that are not solutions. Or we want as few as possible points of this kind. The other one does this job quite well, but the problem is that it's too difficult to check in practice. So we want conditions that are easy to be verified, and maybe more important, this condition, you can't check this condition in practice. You are not able to build an affordable algorithm that generates a sequence that converts to a local minimizer. So we want conditions that we can verify in practice with an affordable algorithm. So in the last lecture we focused on sequential optimality conditions. There were conditions of this kind. It says that there exists some sequence xk converging to this point x, such that some property of the sequence holds. So with this, we were able to define some stopping criteria. But this lecture, we will comment on more classical optimality conditions of this kind. We call this punctual optimality conditions. They depend only on the point x that that's the local minimizer that we want to analyze. So it's typically of this form. If you have a local minimizer and some condition on the feasible set that we call constraint qualification, then you get KKT conditions. So we write this in this form just to get an optimality condition. And what is important to notice here that we want weak constraint qualifications. I will call this CQs. The weaker the constraint qualification, the stronger the optimality condition will be. Okay, so let's begin with this picture. We have this feasible set. It's defined by two inequality constraints. And let's assume that this vertex here is the solution of the problem. Okay, so I want to describe what should happen to the gradient of the objective function. So we can compute this cone. It's the tangent cone. Okay, so we build this cone in the following sense, in the following way. This cone is formed by every limiting direction of sequences that converge to this point x, of feasible sequences that converge to this point x. So if I take a sequence of points here converging to this point, the limiting direction belongs to this cone. If I come from this border here of the feasible set, I get this green direction in the tangent cone. Okay, I will write down the formal definition in a minute. So what should happen to the minus the gradient of the objective function if this is the solution? It should happen that the function is decreasing at this direction. Okay, if this is the solution, the objective function wants to decrease if I walk to this side of the feasible set. In other words, it should increase at this direction. So I can say that something like this should hold. Minus the gradient of the objective function points somewhere around here. Okay, minus the gradient points at directions that decreases the objective function, so all these directions should decrease. In other words, if I look at directions pointing inward the feasible set or the tangent cone, the objective function increases. Okay, so this is what is called the geometric optimality condition. And what it says that minus the gradient of the objective function must form an angle of greater or equal to 90 degrees with every direction in the tangent cone. Okay, this is intuitively correct, and we can give a short proof in a minute. So just let me state the theorem in a little bit more details. I'm saying that if I have X, a local solution, then this inequality should hold for every direction in the tangent cone. Okay, this is saying that the directions in the tangent cone forms an angle of larger or equal to 90 degrees with the gradient of minus the gradient with the directions, all directions in the tangent cone. And the tangent cone is this geometric object. You can artificially add 0 here, and you add any other direction if this happens. If you are able to find a feasible sequence, xk, converging to this point x, and if you take the limiting direction, it's something like this, xk minus x, and I want to look only at the direction, so I divide by the norm. This always has a convergent subsequence, and okay, this direction, I call it a normalized D. Okay, so every direction D with this property belongs to the tangent cone. I can talk about this condition in this other way. I can define the polar of any cone, in particular to the tangent cone, in this way. It's the set of directions that forms angle greater or equal to 90 degrees with every other direction in the cone. So I can state this, the geometric optimality condition, like this. Minus the gradient belongs to this cone. And it's this red cone here that I draw. So the proof is simple. So let's take a direction D. That D belongs to the tangent cone. So I'm assuming that X is a local solution, and I want to prove this. So for every direction in the tangent cone, this should hold. So for the direction 0, this is trivial, but for a non-zero direction D, so since it belongs to this cone, there must exist a feasible sequence, xk, converging to x. So what happens here is that f of x is less or equal to f of xk if I take k sufficiently large. Okay, because x a local solution. Since xk is feasible and it's getting arbitrarily close to x, this should hold. And now I simply take a Taylor expansion here. Something like this. Okay, and plus an error term, O of xk. And these terms goes to 0 faster than xk minus x goes to 0. So I simply divide by the norm here. I can get rid of this. And I simply divide by the norm here. Okay, so this sk goes to infinity, this goes to 0, and this goes to the direction d. So I have this inequality. Okay, so this is what is called the geometric optimality condition. But the difficulty here is that this tangent cone is not easy to be computed. It's a purely geometric object, and an algorithm cannot look at this cone. And nor is it polar. The polar is at least as hard to build as the tangent cone. So, but what we can do then is to design an approximation to this tangent cone. And a very good approximation to the tangent cone is the linearized cone. This is simply the set of first-order feasible directions, as we have talked earlier. So it's the directions that are orthogonal to all the gradients of equality constraints and that form angle greater or equal to 90 degrees with every active constraint. And it turns out that its polar can be computed. Maybe not as easy as it's written here. But you can compute its dual, its polar. You have to use linear programming duality or Farkas lemma. That's an equivalent tool. So with this, you prove this statement. The polar of the linearized cone is given by this set. So we call this set the set of positive linear combination of the gradients. So it's a linear combination of all the gradients of equalities and active inequalities, but the sign here of these scalars are non-negative. Okay, so we call it this a positive linear combination of vectors. And okay, so for this problem, we have, this is the tangent cone, and this is the linearized cone. We see here that the gradients of these active constraints are perpendicular to the curve. So the set of directions, this first inequality defines a linearization that is this half line, everything below this line. And if I linearize this other one, it gives everybody above this line. So you can prove that they are the same. And in fact, in every time, if you look here at the point, and you can take directions that point inward the feasible set, if you have here a whole set of directions, not only one, you are able to, you can prove that the tangent cone and the linearized cone are the same. Okay, so let me show you another example. If you have this problem, the feasible set is this two set of lines. So you have x1 should be greater or equal to 0, so you have here the first order, x2 is greater or equal to 0, but this constraint says that either x1 or x2 should be 0. So you are constrained here to these two lines. Here, this is not feasible set. So what's the tangent cone here? It's the set of if you are looking at this point here, the 0, 0. So the set of directions that you can get by feasible points are these, only these ones. Okay, you can't get these directions inside by converging to feasible points. But when this is the polar, okay, this is the set of directions that are that form angle greater or equal to 90 degrees to every other every direction in the tangent cone. You get this whole cone. And if you compute the linearization of this constraint, this equality constraint plays no role here. The linearization does not constrain the direction in any sense. So you get only the linearization of these constraints. They are already linear, so you get this whole tangent cone. This is the linearized cone, this filled cone here. It turns out that the cones are not equal. The linearized cone and the tangent cone are not equal. But if you compute the polar, they are equal. So remember, the geometric inequality, geometric optimality condition said that minus the gradient should belong to the polar of the tangent cone. So if it's the only important thing is that the polar should be the same, and this happens for this problem. Okay, but you can have a situation where the polars are not equal, and this is a constraint set where this happens. So here, the tangent cone is this green line. See that these curves are tangent here, so the only way to get to this point through a direction is if I come from this side. And the polar is this half space. But the linearization of this constraint is this whole line here. This constraint here is an x cube, y less or equal to x cube. So it's something like this, and this is y greater than minus x cube. So it's something like this. When I linearize this constraint, I get this whole line. And when I linearize this other constraint, I get this other line, above this line and below. So I have this, this is the linearized cone. And the polar of this is simply this line here. So it's not equal to the polar of the tangent cone. In fact, you can always prove that the tangent cone is a subset of the linearized cone. So, but you can't prove equality. Okay, so let's see what we get if the polar of the tangent cone is the same as the polar of the linearized cone. The geometric optimality condition is this: minus the gradient belongs to the polar of the tangent, that is equal to the polar of the linearized, and it's this set, okay? So this is precisely the KKT condition. So minus the gradient of f at the solution should be a positive combination of the gradients of the active constraints. So if I move this minus the gradient to the other side, I get this. Okay, this is a constraint qualification. Okay, if the polar of the tangent is equal to the polar of the feasible, of the linearized, we get that at the solution the KKT condition holds. Okay? So it's, what I want to do is to show you some other conditions that has this property. So we have already seen that a sufficient condition to ensure KKT conditions is linear independence. So in fact, every constraint qualification will be used to prove that the polar of these cones are the same. So a constraint qualification is any condition at a feasible point x, or you can think of it as around a feasible point x, and it's a condition on the functions that define the feasible set, not the feasible set in itself. So this condition must be in such a way that the KKT condition should hold whenever x is a local solution. And the objective function should not play a role here in this formulation. So the constraint qualification is a property of the description of the feasible set. And it turns out that this condition, the equality of the polars, it's called the Guignard constraint qualification in 69. It turns out that this is the weakest possible constraint qualification. So there is a paper by Gold and Toll in 71, and they prove that if you have a point x, and let's take every objective function f in such a sense that x is a local minimum to this problem. So the constraint set omega is fixed. We have this fixed point x, and I want to look at every objective function such that this problem has a local minimum, a constrained local minimum at x. So Golden Tool proved that this point is a KKT point if and only if this constraint qualification holds. So KKT condition is equivalent to Guignard constraint qualification if you want this to hold for every objective function. So in this sense, this constraint qualification is the weakest possible constraint qualification. So maybe you should say, okay, there is nothing else to say about constraint qualification. This is the best one. We are done. The difficulty here is that we can't build algorithms that if you impose this condition to your problem, you can't build an affordable algorithm that will generate KKT points. In fact, you need stronger assumptions if you want to build an affordable algorithm. So what our study in our group was in the sense to develop stronger constraint qualification, stronger than this, but weaker than the ones that are usually applied to proving convergence in algorithms. Usually in many algorithms, the authors assume linear independence. So it's a typical hypothesis. If they want to prove convergence to a KKT point, they assume that linear independence holds. But this may be too strong for some applications. There are classes of problems where no problem fulfills the linear independence constraint qualification. So you can't apply these well-known algorithms for this class of problems. So we should define weaker ones. So this is what is written here. Maybe I should remind you that KKT is not an optimality condition without any additional assumption. There is an example here. We have already talked about that. So let me show you a lot of constraint qualifications. There are a lot of names. They are similar to each other. They rely on linear independence or maybe positive linear independence, as we said before. But there are a lot of names. Maybe you will get a little bit confused, but you don't have to remember every name here. So the simplest constraint qualification is the linear independence constraint qualification, LICQ. Sometimes it's called regularity. So it simply says that at the solution at a point x, if I look at the gradient of the active constraint, the equality and the active inequalities, and if you put them together in a single set, this should be linearly independent. So it's interesting about this constraint qualification that if you assume this, you can prove that if you have a solution that fulfills this condition, there will be only one set of Lagrange multipliers. It's associated to this point. There is a unique Lagrange multiplier to this problem. So it's easy to work with algorithms that generate approximations to Lagrange multipliers. So this will not be the case for other conditions. So just to show you how we can generalize this condition, we note that assuming that this set of gradient is linear independent, you could think that this is a condition on the point x, but in fact you are constraining a whole neighborhood of the point x, because if this set of gradient is linearly independent, since these gradients are continuous, in a neighborhood of this point x, these vectors will remain linearly independent. So when you assume linear independence, you are constraining a whole neighborhood of the point to have linearly independent vectors. And maybe this is too strict. And another thing, you are constraining not only the whole set of gradients, but you are constraining every possible subset of the gradients. So if I don't take here all the grades, but if I choose a subset, I will add here only the gradients on some subset I and some subset J of the active constraints. This set of gradients should also be linearly independent. Okay, this is because every subset of a linearly independent set of vector is also linearly independent. So in fact, you are assuming this. For every subset of equalities and every subset of active inequalities, the set of gradients is linearly independent in a whole neighborhood of this point x. Okay. So with this in mind, it turns out that we can generalize this and we don't need to ask linear independence in the point. So there is this nice paper by Janin, 84, where he defines the constraint qualification called the constant rank constraint qualification. So it reads in this way. If for every subset of equalities and for every subset of active inequalities, you don't need linear independence in this point, but if this set of vector is linearly dependent, then they must remain linearly dependent in a neighborhood. Okay, so this is what we call a constant rank constraint qualification, and this is equivalent to saying that this set of vectors has the same rank. For every possible subset, the rank of these vectors does not change in a neighborhood. Okay, so it turns out that if you have linear constraints, maybe if you look at all the active constraints, you don't have linear independence of the vectors, but if they are linear dependent, if the gradients are linear dependent, in a neighborhood they will remain linearly dependent because they are the same. Okay, it's a linear constraints, the gradients does not vary with x. So you have this property of maintaining linear dependence in a neighborhood. So it turns out that it's a well-known result that for linear constraints, you don't need linear independence in order to prove existence of Lagrange multipliers. So this is mainly the reason for this. You can generalize this to nonlinear inequalities in this sense. Okay. So let me show you some other constraint qualifications. Remember I told you maybe yesterday about the Mangasarian-Fromovitz constraint qualification. And the idea here is that the right concept is not linear dependence or linear independence. It's positive linear independence or dependence. This is because we want to take advantage of what we know, that in the KKT conditions, the Lagrangian multipliers should be non-negative associated to the inequality constraints. So this is the right concept here. So we have m plus p vectors in our Rn, and we say that this object here, it's a pair of tuple of vectors. This pair is positive linearly dependent if you are able to find scalars that are not all zero, and scalars associated to the second tuple are non-negative, and the linear combination are zero. So it's a concept very similar to linear dependent, but we are asking that for the second tuple of vectors, the scalars should be non-negative. So if this not holds, we say that these vectors are positive linearly independent. So it's clear that linearly independence is a stronger concept. If you have linearly independency of some vectors, of course it says that there does not exist any scalars, no matter the sign, such that the linear combination is zero. So of course there will not exist these scalars if I'm looking only at non-negative ones. So this implication holds, and this concept is so it's a weaker assumption if we assume positive linearly independence. And this is what is done in the Mangasarian-Fromovitz constraint qualification from 1967. We say that this set of vectors, or this pair of tuple of vectors, is positive linearly independent. We look here at all the set of gradients and all the set of active inequality gradients. So we do this, we require this. So let me give you an example where this holds and where the vectors are not linearly independent. So if I have two inequality constraints that are the same, okay, maybe this could happen, or at least the gradients are the same. Okay, maybe the functions that define the feasible set are not the same, but the gradients are the same. So if I compute here a linear combination, let me write it down. So I want to look at the combination of this form. Gradient of G plus the gradient of G should be 0. So these are not linearly independent vector. If I take alpha equal to minus beta, you see that these are linear dependent. But if I look only at alpha and beta greater or equal to 0, this is equivalent to this alpha plus beta. Gradient of G of x is 0. And if I assume that this is a non-zero vector, I will have that this is 0. So you have a sum of two non-negative numbers. You should be 0. So the only solution is if we take alpha and beta equal to 0. So this is positive linearly independent. So it turns out that it's not a problem if you have, if in your formulation you have gradients that are the same at the solution, or if you have the same constraint repeated in your model. And this is important. The idea here is that we want to give more freedom to the one that is modeling the problem. We don't want him to worry about possible redundancy in your constraint. So the constraints are what they are, and we want to be able to prove that it's okay. This formulation is okay. The solution will be a KKT point. So another example where this holds is when you are able, if you have only inequality constraints, if you are able to show that there exists a direction D that points inward the feasible set, something like this, at this direction, the gradient, the function G decreases, and if this direction holds for every active constraint, so this is, in this case, the Mangasarian-Fromovitz holds. Okay, so that's why I said in the beginning that if you can find the direction that points inward the feasible set, the cones will be the same. Okay, it's because this constraint qualification will hold. Okay, so in the same way as we have done with linearly independence, we can describe this condition in this way. The concept of positive linearly independency, if it holds at a point, it also holds in a neighborhood of this point, because these gradients are continuous. So we can show this. Asking positive linear independence in the point is the same as asking in a whole neighborhood. And if you have subsets, they are also positive linearly independent. So in fact, you are asking something like this. So if you want to ask something weaker than this, we should look at all these subsets and replace this positive linearly independency. And the idea, this came from 2000 by Key and Wei. They defined this condition called the constant positive linear dependence condition. So it's the same idea as the work of Janning. You simply replace positive linearly independence by constant positive linearly dependence. So you don't need to ask that this set of gradients are positive linearly independent. But if they are linearly dependent, they must remain positive linearly dependent in a whole neighborhood. Okay, so it's a straightforward generalization. So this was done in 2000. They defined this condition and used it in some algorithm, in some SQP algorithm. And in our group in Campinas, they proved that in 2005 that this is in fact a constraint qualification. Okay, and they did that, and they also proved that the augmented Lagrangian generates KKT point under this condition. So to our knowledge, this was the first time where we were able to design an affordable algorithm such that its theory of convergence was not based on linear independence or Mangasarian-Fromovitz constraint qualification or constant rank condition. So this is weaker than all the other conditions.
Yes, one question. When you mentioned that the augmented Lagrangian will satisfy this constraint qualification, do you mean any implementation of the augmented Lagrangian or the specific implementation you did in your group?
It's we only looked at our specific implementation, but I think it should hold in general. And one case where this condition holds and the Mangasarian-Fromovitz condition does not hold is when you have this set of constraints. You have age of x less or equal to 0, and you have minus age of x less than or equal to 0. And this case appears a lot in practice. Maybe your solver only allows inequality constraints. So if in your model you have equality constraints, you can separate these equality constraints into inequalities in this way. So this is equivalent to saying that age of x is equal to 0, and this is usually done in practice. But if you do this, what you get is that if you add the gradients, if you have the gradient of age plus the gradient of minus age, you will get 0. So these are positive linear dependent vectors. Okay, you have the scalar is 1. Maybe I should write it down. You have alpha gradient of age plus beta gradient of minus age. This is 0 if you take alpha and beta equal to 1. So this is positive linear dependent, and if you want to solve this problem with a solver that its theory is based on MEFCQ, you don't have a guarantee that you will find a solution. Okay, so MEFCQ does not hold. Okay, but if you are using a solver that is based on the CPLD condition, you are safe. Okay, look that they are not positively linearly independent, they are positively linearly dependent. But if I look at the neighborhood, this equality holds as well. If I change the point x to some point y, the gradients are the same, and they will remain positively linearly dependent in a neighborhood. So you are safe. It turns out that if the important key is to ask positive linearly dependent on the point x, but when you look at the neighborhood, it's equivalent if you ask positive linearly dependence or linearly dependence. So it's the same. It doesn't matter if you add here positive or not. So a more recent work on the relaxed constant rank constraint qualification, it was done by Minchenko and Stakovsky in 2011, and I was studying this during my postdoc, and I saw this work by Minchenko and Stakovsky. And what they did, they proved this. Remember, the constant rank condition by Janin is this. Okay, you have to look at every subset of equality constraints and every subset of active inequality constraint, and linear dependence should be maintained in a neighborhood. So, as I mentioned, this is equivalent to ask that the rank is the same in this neighborhood. So what Minchenko and Stakovsky did, they proved this weaker condition. They show, well, in fact, you don't need to look at every subset of the equality constraints. You only need to look at the whole set of equality constraints, and this is enough. This will be a constraint qualification. Okay, so this is quite important result, because it's hard to check these conditions. They are hard enough to check, and if you need to check it for every subset, it's harder. So they simplified the condition a little bit, and maybe I should show you an example. You have here one equality constraint, two inequalities, and you are looking at the origin. So these are the three gradients at any point x, y. And since I need to, for the constant rank, the classical constant rank condition, I need to look at every possible combination of this, every possible subset of these three. And so if I look at these two, look at the origin, this set has rank 1. Okay, this set is, these vectors are the same. But when I change to a neighborhood, this set now has rank 2. Okay, so these are the constant rank condition fails. But the relaxed constant rank condition asks me to look only of subsets that include this equality constraint. So when I include this, I don't have a problem. The rank is always 2, and in the neighborhood, it remains 2. So it holds here. So my work in the postdoc was to develop something similar to the relaxed constant rank condition, but by looking at positive linear dependency. So it's quite straightforward idea, but not so easy to implement. So this is published in a paper in Matemática programming, and I will give you the reference in the end. So it turns out that the correct generalization of the constant positive linear dependence, we call this relaxed CPLG, is the following. For the equality constraints, you should ask that they have the same rank. Okay, you can't get rid of this rank condition when you look at equality constraint. The full set of equalities should have the same rank in a neighborhood. And here you can't use the whole set of equations, the whole set of equality constraint gradients, but you have a fixed set. So you don't need to check for every subset, you need to check it for a fixed subset, and this fixed subset, you can choose it in this way. Any set of constraint that fulfills this condition. At the point x, this should form a basis for the space generated by the whole set of constraints. So I look at all possible linear combinations of these vectors, and I should be able to generate them using linear combinations of this one. So this all, if this set of vectors is linearly dependent, you can always find a smaller subset with this property. And what we ask here is, for this fixed subset of indexes, you ask what you must imagine we ask. For every subset of active constraints, if I add here this fixed set with this varying subset, if this is positive linearly dependent, then this must remain linearly dependent or positive linearly dependent. It's the same, it's equivalent in a whole neighborhood. Okay, so we define this condition, and in this paper we also proved that the augmented Lagrangian goes well with this constraint qualification. So we proved that it is weaker than all the previous ones that I showed, and it's strictly weaker. We have examples showing that it's not the same as any other one, but the augmented Lagrangian goes well with them. That's the main result. So maybe I should show you an example. We have here again one equality constraint and two inequality constraints. These are the gradients at any point x and y. We are interested in looking at this condition at the point 0, 0. And the CPL, I'm going to check that CPLG fails. So CPLG asks for positive linear dependency, for a constant positive linear dependency in every subset of these gradients. So in particular, if I take this third one and this one, okay, this at the origin, it's this vector 0, 2, 0, minus 1, and this is positive linearly dependent. I can get the 0 vector by using these positive scalars. But in a neighborhood, it turns out that you can't do this. Okay, these vectors are in fact linearly independent, so you can't get positive scalars such that this return 0. So the CPLD fails. So if it fails for one particular subset, it simply fails. But if you want to check the relaxed CPLG, this gradient that corresponds to the equality constraints should always be included when we check this kind of condition. So when we include this, it's -2, 0. It remains positive linearly independence. We simply add 0. We use 0 here as the scalar, so it's positive linearly independent. But if I look at the neighborhood, you have 3 vectors in R2. This should be linearly dependent. So in particular, the relaxed CPLG holds for this was the only critical case. I should check also if I add this vector and this and this and this, and but okay, this is easy. This is the same. So this is in fact a weaker condition. Okay, so after we did that, after we defined this relaxed CPLD, we started to think about, okay, we were able to get rid of verifications for every subset of the equality constraints, but this is a little bit annoying. For the inequality constraints, we still have to look at every possible subset. So this is true for the relaxed constant rank, and this is true for the relaxed CPLD, okay, for every subset. I think I'll take a break here. Okay, we start again in a few minutes.
Let me make a quick question before that. Is there any result relating how far are we getting with these conditions from the weakest one? So we are getting weaker and weaker constraint qualifications. There is the difficult one to check, which you mentioned in the beginning. Is there any study that maybe with some additional assumption on the functions, differentiability or something like that, we can get equivalence or something like that?
No, I've never seen any result in this sense. We only prove that it's another constraint qualification in the middle of this implication, but in fact we don't know how far we are.
Continuamos entonces en 10 minutos.